Hello, this is Terry again. Today I want to share with you another very interesting problem. It's Euler's solution to the Basel problem. So first, very quickly, a summary of the Basel problem. By the 14th century, the harmonic sum of 1 over k, k runs from 1 to infinity, was already known to be divergent. To the best of my knowledge, it has something to do with a French mathematician, Nicole Oresme. I believe he showed that this was true. Then by 1650, the Italian mathematician Pietro Mingoli wanted to know, well, okay, if the sum of 1 over k, right, the infinite series of 1 over k is divergent, what about the infinite series of 1 over k squared? He wanted to figure out what the answer was, but he couldn't figure it out. Then since then, many well-known mathematicians like Wallace, the Bernoulli brothers, Goldbach, and others have attempted to trying to solve it, and none were successful. Then two things happened. The first thing was in 1731. Leonard Euler came along and he showed how to improve the approximation. It was quite amazing. The improvement itself to the approximation was quite amazing. But a few years later, in 1735, he actually came forward and said, you know what, forget the approximation, right? He has the exact value of the series. That was just amazing. So anyway, so this problem has since been known as the Basel problem, named after the city of Basel in Switzerland. A lot of my understanding of the material of this problem came from this paper. So if you're interested, read this. This is really a great paper. It's published by the Mathematical Association of America, the Dolciani Mathematical Exposition, number 22. Title Euler, the Master of Us All. This is really a great paper written by Dunham in 1999. All right, so let's start by first focus. So in this video, we're gonna do two things, right? We're gonna first show how he improved the approximation part, and then in the second part, we'll show how he proved the exact answer. So before Euler's solution, right? As I said, a lot of people try to estimate its value. Unfortunately, this problem, as an approximation problem, is actually difficult. Why is it? It's difficult because essentially your summand 1 over k squared, it's decreasing too slowly, right? So think about it. When k is equal to 1, you're adding 1. When k is equal to 2, you're adding a fourth. 1/4 is what? 0.25 in numerical value, right? When k is equal to 3, it's 1/9. What's 1/9? That's point, what is it? 1, 1, 1, 1, 1, 1, and so on, right? The point is, as you increase k, right, starting from 1 to 2 to 3 to 4, each of these is decreasing too slowly. So another way of thinking about being slowly is that it's contributing to the overall sum still by too much, right? So here's an example. So I want to show you, just to give you a sense of what we're dealing with. Using the answer that Euler had provided to us, we know the answer using modern computing, right? We know the answer is approximately 1.66493. 1.64493, and so on. Now imagine I were to sum this 1 over k squared, k running from 1 to n, right? When n is 10, so in other words, if you add up the first 10 terms, you're only up to 1.53977, not even, right? When n is 100, it's 1.63448, still not quite there yet. So when n is 1,000, it's 1.6439335. And then when n is equal to 10,000, that's when you get to like 1.644, right? 83. So even when n is 10,000, you're only accurate up to 3 decimal places, right? You're not even accurate up to 4 decimal places yet. That's just to show how difficult, this problem is as a numerical approximation, because this thing converges way too slowly. So Euler did something remarkable. In 1731, he showed how to improve the approximation as follows. What he did was, he considered the integral minus log of 1 minus t over t integrating from 0 to 1/2. Okay. Now remember, Euler, by the time he worked on this, he knew of the series expansion of natural log of 1 minus t, which was what? Minus t squared over 2 minus t cubed over 3 and so on. And this series is valid for all t greater than -1 and less than +1. Right? So now he's trying to attack this integral from the series angle. What do you do? He said log of 1 minus t, let's replace it with this series. Remember, he knew this series valid between -1 and 1. And since he's integrating from 0 to 1/2, that's well within this interval. So he knew this series in this interval of integration is valid. So he replaced it. He replaced log of 1 minus t with this series. Then now he divided term by term, right? So this gives us, by the way, there's a minus here, right? And then each of these is a minus, so the minus cancel out. So you get a positive integral from 0 to 1/2. T over t, 1. T squared over 2 divided by t, t over 2. Right? T cubed over 3 divided by t is t squared over 3, and so on. This infinite series. Then he integrated term by term and get this t plus t squared over 4 plus t cubed over 9 plus t to the 4th over 16 and so on. Evaluated from 0 to 1/2. Now, some of you here might say, well, wait a minute. How does he know integrating term by term is valid? Keeping in mind, this was the 18th century. This is 1731. So, again, if my knowledge of mathematical history is accurate, this kind of question were important, but it wasn't really like fully addressed until the next century, right? Until the 19th century. So given that this is Euler being Euler, let us give him the benefit of the doubt. Let's assume he actually checked this. Let's assume he knew what he was doing, and so this is fine. So let's assume this is okay. So just continue, right? So our focus is not on this, obviously. So when you evaluate this series, what happened? Well, first notice at 0, you don't need to worry about it because everything here will go away, right? Because all of these involve t, so when you evaluate 0, it's all gone. So let's just focus on 1/2. What is it when it's 1/2? Well, plug it in. 1/2 plus 1/2 squared over 4 plus 1/2 cubed over 9 plus 1/2 to the 4th over 16 and so on. You can rewrite this as follows. 1 over 1 squared times 2 to the 1 plus 1 over 2 squared times 2 to the 2 plus 1 over 3 squared 2 to the 3 and so on. So if I were to write this in series form, this is just the infinite series of 1 over k squared times 2 to the k, right? Or 1 over k squared 2 to the k. Let's call this integral with this series answer as equation number 1. Okay, so here's what he did. So he started with this integral and he attacked the integral using the series approach. Then the next thing, he's trying to attack the integral again, but this time directly using integral by expanding a different way. So he already knew of the geometric series, right? Of u to the k run from 0 to infinity is 1 over 1 minus u, so long as u is greater than -1 and less than 1, right? He knew of the geometric series. And so from the integral angle, right? So by replacing this 1 over t, somehow related to this geometric series as follows. Let u equal to 1 minus t. So of course du is minus dt, so keep that in mind. Then the negative integral from 0 to 1/2 of log 1 minus t over t is going to be the integral of 1 over 1 minus u, because 1 over t becomes 1 over 1 minus u. Log of 1 minus t becomes log of u. And when t is equal to 0, right, u is equal to 1. When t is equal to 1/2, u of course is 1/2. So this new range, new range of integration is going to be from 1 to 1/2. And of course the minus dt, this minus dt becomes just du. So this is a simple substitution problem, right? Now, then the next thing he did was he said, let's use the series approach again, but this time let's use a different series, use geometric series. 1 over 1 minus u is the same as this geometric series. So he replaces it with 1 plus u squared plus u cubed and so on, all multiplied by log u du. There's integral of this series, right? Now, keeping in mind, right, he knew he can do this because this is like technically a improper integral, but let's set that aside for a minute. So imagine you're integrating from 1 minus, 1 minus epsilon or something. So let's not worry about the improperness of this yet. So this right? When you make this substitution, it's going to be 1 to 1/2 of this integral. Now multiply them out. So now this integral, the integral of this series, becomes a series of the integral. So again, some of you may say, wait a minute, right? Integral, series, integral. Again, keeping in mind, let's assume he checked this and it's fine. So let's not worry about that. Let's continue. So when you integrate this term by term, you're going to integrate u to the k, right? So remember, if you turn this into a series, so this now become a summand. So u to the k log u du. What is that? Term by term, this is just u to the k plus 1 over k plus 1 times log u minus u to the k plus 1 over k plus 1 quantity square. And you're going to evaluate it from 1 to 1/2 and then sum. So evaluate and then sum. Now here's what he did. He did two things next. Instead of working with the index k equal to 0 to infinity, he's going to work with j equal to k plus 1. By letting j equal k plus 1, now j runs from 1 to infinity. So this now becomes 1 to infinity. So that's the first thing he did. So he replaced anything with k plus 1, he replaced it with j. So this becomes u to the j over j log u minus u to the j over j squared, right? So that was the first thing he did. Second thing he did was this series of, so instead of evaluating the summand and then sum, he swapped the operation. He summed them first, then evaluate. Right? So now let's look what happened if you do that. So when you sum this, right, what do you get? Iterating, when j equal to 1 is u log u minus u. When j equal to 2 is u squared over 2 log u minus u squared over 4, and so on, plus dot, dot, dot. This is now an infinite series. Then evaluate from 1 to 1/2. Right? Now, inside this square bracket, let's regroup some stuff. You notice here that every other term contains a log term. Let's group them. So u log u, for example, plus u squared over 2 log u, and so on. This becomes log u times u plus u squared over 2 plus u cubed over 3 plus dot, dot, dot. Then the other term, that the rest of the terms that do not involve log u, group them together. Right? So they all, since they're all minus, so just factor minus out minus the quantity u plus u squared over 4 plus u cubed over 9 plus dot, dot, dot. All of these you evaluate it from 1 to 1/2. Now, looking at this, right, you notice something about this guy right here. U plus u squared over 2 plus u cubed over 3. What is that? That is just the negative of log 1 minus u. Remember, because he knew of the series expansion of log of 1 minus u, which is the negative of this series, right? So this, he replaced this series now by minus log of 1 minus u. Okay? And then the rest of these stay exactly the same. So you're going to get this. So this now becomes minus log u times log of 1 minus u minus this series. All this evaluated from 1 to 1/2. What is that equal to? Well, let's start with the upper limit. When u is equal to 1/2, you're going to get minus log 1/2, right? And this 1 minus 1/2 is 1/2. So this is actually minus the square of log 1/2, right? Minus the square of log 1/2. And plugging in this series, 1/2, what do you get? You're going to get 1/2 plus 1/4 over 4 plus 1/8 over 9 plus dot, 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 right? Sounds familiar? We've seen this before, right? Then what happens at 1? Now, he did the limit, right? I mean, to the best of my knowledge, I could be wrong, and if some of you disagree with me, let me know. But from what I understand, I don't think he actually, at least from what I read, I don't think he justified this. But, you know, he knew of it. Somehow he just dropped this term. At 1, this term vanished, basically, okay? But today, we know why that's the case, right? You can justify this by taking the limit as u goes to 1, log u times log of 1 minus u. That is, in fact, 0. So using modern limit theory, we do know that is 0. So he was correct to just go ahead and ignore this term when this is 1, when u goes to 1. So that's gone. Now, what's next? Minus the negative of this, plug in 1. That's just plus, right? Because minus give you a plus, 1 plus a 4th, plus a 9th, plus dot, 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 because u is 1. By plugging here, you get this series. This is the series we're after, right? Of course. So let's combine them and kind of clean it up. This becomes minus the square of log 2, right? Because log 1/2 is negative log 2. But remember, you're squaring the negative inside, so it becomes positive log 2. And then there's a negative sign outside, so this is minus square of log 2. Okay? This is the series we have seen before. Is that sum of 1 over k squared to the k running from 1 to infinity. This, of course, is just sum of 1 over k squared, k running from 1 to infinity. This is the series we are after. Let's call this equation 2. So now what has he done? He had use two different ways to calculate the same integral, right? Equation 1 right here and equation 2 right here. They're the same thing. They're pointing to the same integral, so they must be equal. So by equating the two, he now has minus the square of log 2 minus this infinite series 1 over k squared 2 to the k plus the infinite series 1 over k squared. That equals to this integral, which in turn equal to 1. So this is the left-hand side is expression 2. The right-hand side is expression 1. That's the sum of 1 over k squared 2 to the k. If these two are equal, right, now you want to solve for the sum of 1 over k squared. So solving sum of 1 over k squared, you move the minus square of log 2 to the other side, you're going to get a positive square of log 2. You move this, remember this series and this series are exactly identical. When you move the negative version from the left to the right, you get two copies. So this is two copies of this series, right? So when you do 2, when you multiply 2 inside, 2 times 1 over 2 to the k, you get 1 over 2 to the k minus 1, right? So this series now is sum of 1 over k squared 2 to the k minus 1. K runs from 1 to infinity. Okay? Great. So now he has this. So how exactly is this better? Watch what happens next. This is the cool part. Understanding that this, remember at that time he already knew of the series expansion of log of 1 plus x, which is x minus x squared over 2 plus x cubed over 3 minus dot dot dot. It alternates in sign and is valid for all x greater than minus 1 and lesser than or equal to plus 1. This is the key. Less than or equal to plus 1. Because this series is actually valid at 1. So plugging in x equal to 1, what do you get? You get log of 1 plus 1, which is log 2. And on the series side, it's just the alternating harmonic sum. 1 minus half plus a third minus a fourth plus a fifth and so on. Now let's think about this for a second. What's 1 minus a half? That's a half. Now if you add a third, that's 5, 6, and then minus a fourth, etc., whatever that is. The point is, because this series is so easy to work with, right? Presumably, you can, even if you have to do it by hand, it's not that difficult to go as far out as you like and get log 2, the approximation of log 2 as a fraction. And squaring the fraction is easy, right? So you can imagine, even if I were to do it by hand, I can approximate log 2 to a very accurate value by just adding out further and further out, and turning into a finite sum and then squaring the finite sum and do long division. Is manageable. The point is manageable, right? Getting log 2 is very manageable, even if you were to do it by hand. Remember, this is the 18th century, right? They didn't have computers, and so you have to probably do it by hand. So, but it's not bad, right? Even if you were to do it by hand, this is not bad. Okay. So really, the only thing that you have to worry about is this series here. Because to solve this, to approximate this series, you're going to approximate this. And we always said this is assuming this is pretty easy to do. It's much more manageable. So it's really all comes down to just how do you approximate this series very accurately, right? And how fast will this, will the summand go down? In other words, how much faster is this series compared to if I were to just iterate this, this series by hand? Well, I did some calculations, so focusing only on this series. So never ignore the square of log 2 for a minute. Here's what it is. Using modern computers, right? At infinity is 1.16448. This series is, remember, not this, only focus on this series, okay? I don't care about log 2 for a minute. The answer is 1.16448. Let's do six digits. 1.164481, let's say, okay? If n is 5, if I add up the first 5 terms, I got what? 1.160590, right? When n equal to 10, I got 1.164447. Look how close it is, right? Then now when n equal to 20, it's 1.164481. Look at that, 1.164481. So in other words, when you add just 20 terms, you're already accurate up to 6 decimal places. That is remarkable. And look what happened when you add to n equal to 30. You get 1.164810.5. Right? You're already 10 places accurate. Is that right? 2, 4, 6, 8, 10. Yeah. 10 places accurate. Only with 30 terms, you already get that accurate. So the point is, let's say if you were to only approximate up to 6 decimal places, literally, I mean, 1464481, you can just stop at n equal to 20, right? Compare that to this, right? Look how many terms you have to add before you get anywhere near that kind of accuracy. So the point is, this was quite remarkable in and of itself. This is a monumental achievement just by doing some math and turn this series of 1 over k squared into this series, right, into log 2 square of log 2 plus this series, where this series converges so much faster. That is amazing. I mean, from a computational standpoint, this was truly a remarkable achievement. Okay, so that was the year 1731. Fast forward a few years, the year 1735. He basically announced that, hey, forget the approximation, right? I know the exact value. It's pi squared over 6. Why is that? So let's see what he did. Again, very remarkable stuff. So amazing. So starting out, he considered the function f of x equal 1 minus x squared over 3 factorial plus x to the 4th over 5 factorial minus x to the 6th over 7 factorial plus dot, dot, dot. Right? He considered this a polynomial of infinite degrees, which if you think about it, it makes sense. If you stop anywhere, right, it's a polynomial of an even degree. So yeah, if you keep on going forever, so it's a polynomial of infinite degrees. Never mind that. So what happens to this function if x equal to 0? So evaluate f of 0. Well, at x equal to 0, plug it in, or starting with the second term, since it involves x, everything drops out. So all you have is f of 0 equal to 1. Okay, so now he knows when x is 0, f is 1. So that means whatever the roots of f are, it's not going to be 0. So 0, don't bother with 0. 0, you will not find the roots because f of 0 is 1. What he did was he wanted to find all the roots of f of x that is not, that's outside. Now, at this point, he already knew of the sine series, right? So he knew what the sine series was. But here's what he did. He said, for all x not equal to 0, observe the following. This is a classical trick. Multiply by x divided by x, right? Classic. Because you're dealing with x not equal to 0. So this is perfectly legit. Now, set aside this 1 over x business for a second. Multiply this x inside. Distribute it inside the numerator. What are you going to get? X minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, dot, dot, dot. Odd degree, right? Odd integer factorial, alternating. That's sine x. Remember, he knew of the sine series. So that's just sine of x, right? So for all x not equal to 0, this is just sine of x divided by x. So he now knows, hey, this function, right, is, oops. Oh, that's odd. Oh, wow. That's odd. Anyway, I hope you can see this. I don't know what happened, why suddenly it turned blue. Anyway, so this series is sine of x over x. So the question he asks is, what are the roots of this function? Now remember, he already knew. Don't bother looking at x equals 0 because this function, right, at 0 is 1. So that's not going to be a root. So where else would the root be? Well, if you look at this representation, where else could it be? Well, it's going to be when sine of x is 0, right? So now watch what he's going to do next. That is so amazing. What he's going to do next is so amazing. He said, okay, I know that for all x not equal to 0, I know where sine of x is going to be 0. I know the roots of sine of x. Remember, don't worry about x equals 0 because the function he's interested in, right, this function does not involve, he knows that f of 0 is 1, so don't bother looking there. So for all other x's, sine of x is 0 whenever x is an integer multiple of pi, plus or minus pi, plus or minus 2 pi, plus or minus 3 pi, and so on. Okay, now, this is what is so cool about this. Okay? He said, if I were to construct the function using only these information, right? This function, f of x, is going to have roots at plus or minus pi, plus or minus 2 pi, plus or minus 3 pi, and so on. Isn't it equivalent to doing this? The product, infinite product, right? Multiplying a whole bunch of products together. First term, 1 minus x, or first factor, I should say. First factor, 1 minus x over negative pi. Second factor, 1 minus x over plus pi. Third factor, 1 minus x over minus 2 pi. Fourth factor, 1 minus x over 2 pi, and so on, right? Why is that? Because when x is minus pi, this first factor is 1 minus 1 or 0. So, of course, f of x is 0. When x is minus pi, right? When x is minus pi, right, this is 1. When x is plus pi, this is 1. When x is minus 2 pi, this is 0. Let me start over. It's a little confusing. Okay, when x is minus pi, this factor is 0. When x is plus pi, this factor is 0. When x is minus 2 pi, this factor is 0. When x is plus 2 pi, this factor is 0, and so on. So by multiplying infinitely many factors in this form that coincide exactly with the behavior of this function f of x at having roots at these points, right? Notice if you group them by 2, so the first pair is 1 plus x over pi, 1 minus x over pi. That's just 1 minus x squared over pi squared. If you group the next two, you're going to get 1 plus x over 2 pi times 1 minus x over 2 pi. That's 1 minus x squared over 4 pi squared, and so on. So there are infinitely many pairs that you can work with. So this becomes an infinite product. Now, those of you who work with series, you know the capital letter sigma. Capital Greek letter sigma is used as a symbol to denote infinite series. Capital Greek letter pi, right? This big pi is used to denote in product, or this is an infinite product. So this becomes an infinite product of 1 minus x squared over k squared pi squared, where k runs from 1 to infinity. This is an infinite product, okay? But he said, wait a minute. They're both pointing to f of x. So these two must be the same. Remember, though this is a second expression, right? He had a previous expression before. Remember, he had this infinite series expression. This infinite series expression is f of x. This infinite product expression is also f of x. They're the same thing. So now he equated two. So he has now related an infinite series to an infinite product. That is so cool. By iterating this, right? 1 minus x squared over pi squared, 1 minus x squared over 4 pi squared, and so on. So this infinite series must equal to this infinite product. Now, this is the part where it might be a little difficult to notice, but it is true. When you're working with infinite product, it's kind of like working with infinite series, right? To understand infinite products, you stop at a finite number of terms or finite product, right? It's just like you have a sequence of finite sum. Using a sequence of finite sum to understand a series, same concept is here. Using a sequence of finite product to understand an infinite product. So if you just take this, right, 1 minus x squared over pi squared, the square term, the x squared term is just negative 1 over pi squared. Now, if you go to two terms, right, so now this becomes a fourth degree polynomial if you multiply them out, right? What is the coefficient of x squared? It's minus 1 over pi squared plus a minus 1 over 4 pi squared. What happens if you do three terms? Same thing. So the point is, if you multiply this out into infinitely many products, infinitely many terms, factors multiplied together, you're going to get a polynomial of infinite degree. But that polynomial has a square x squared term. What is the coefficient of that x squared term? As it turns out, is this. If you do the finite, if you start work with the finite product, you'll begin to see a pattern. Is negative 1 over pi squared, minus 1 over 4 pi squared, minus 1 over 9 pi squared, and so on. So if you factor minus out, this becomes negative, this coefficient, 1 over pi squared plus 1 over 4 pi squared plus 1 over 9 pi squared plus dot, dot, dot. This guy is the coefficient of x squared. Okay? Now, but this thing equals to this infinite series, right? Now, looking at this infinite series, you say, hey, what is the square term, right? What if you look at the infinite series, what is the coefficient of x squared? Is minus 1 over 3 factorial. Looking at this infinite product, what is the coefficient of x squared? Is minus this infinite series. They must be the same. So therefore, negative 1/6, remember, because the x squared term on the series side is minus 1 over 3 factorial, which is minus 1/6. On the product side is this infinite series, right? Notice this infinite series, they all involve 1 over pi squared. Let's factor them out. So that's just minus 1 over pi squared times this this infinite series. But this is the infinite series that we're trying to solve. That's minus 1 over pi squared times the infinite sum of 1 over k squared. K runs from 1 to infinity. Okay, so solve for this infinite sum, or infinite series. What do you get? You multiply negative pi squared on both sides. Negative and negative cancel. All you have is pi squared over 6. He had now proved this infinite series that we're trying to figure out, 1 over k squared, k runs from 1 to infinity, is pi squared over 6. So he now gave you an exact answer. Not an approximation, but an exact answer of this infinite series. That was unbelievable, right? So anyway, I hope, you know, I hope you like it as much as I do. For me, this was just amazing. All right, notice one more thing. Not impressed yet. Remember Wallace product? Remember a while back I did a video on proving the Wallace product, you know, by working through the integral of the sine to some power, right? Okay, that was one way of doing it. But here's another way. You could have used Euler's approach to actually prove Wallace product. Here's how it works. Remember, Euler, you know, defined this sine of x over x as we express it as an infinite product, right? 1 minus x squared over k squared pi squared. What happened if you let x equal to pi over 2, right? When you let x equal to pi over 2, this infinite product is just the product of 1 minus pi squared over 4, all divided by k squared pi squared. Pi squared and pi squared cancel. You get infinite product of 1 minus 1 over 4k squared. Iterate this. When k equal to 1, 1 minus a 4. When k equal to 2, 1 minus 1/16. When k equal to 3, 1 minus 1/36, and so on. What's 1 minus a 4? 3/4. What's 1 minus 1/16? 15/16. What's 1 minus 1 over 36? 35 over 36, and so on. The bottom, right? Now look at the top. 3, 15, 35, 63. They are 1 times 3, 3 times 5, 5 times 7, 7 times 9, and so on. The bottom, 4, 16, 36, 34 is 2 times 2, 4 times 4, 6 times 6, 8 times 8, and so on. Now you room together is 1, 3, 3, 5, 5, 7, 7, 9, dot, 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 over 2, 2, 4, 4, 6, 6, 8, 8, dot, dot, dot. Right? So that's just f of pi over 2. But f of x is also sine x over x. So when you use the sine x over x, using knowledge of sine, what happens when you plug in x equal to pi over 2? Well, you're going to get sine of pi over 2 over pi over 2, which is the reciprocal of pi over 2, or 2 over pi. These two are the same thing. This f of pi over 2 and this f of pi over 2 is the same thing. So you equate the two and take the reciprocal. Guess what? You get the Wallace product. That's it. Pi over 2 equal to all these over this. 2, 2, 4, 4, 6, 6, 8, 8 divided by 1, 3, 3, 5, 5, 7, 7, 9, both, you know, infinite product. You prove the Wallace product. So using Euler's approach, you could have also proved the Wallace product. Anyway, this is the end of the video. Just thought I want to share with you. It was something amazing to me. I hope you find it equally interesting. So thank you for watching.